Hi guys, how are you doing? I'm fine, and I'm recording this video also to share with you with some of my recent thoughts about groups and what is action. And I find it really interesting what I found, and that's why I'm sharing it with you. It is also as usually it happens with me. Is that this my thoughts is not might be not really detailed and might not be formal, but it's at least interesting. Yes. And in this time, I'd like to share this link for the video for this translation in my Instagram so some people can see it. 1 minute. Let me do it one. Take not much time. Hmm. Translation. Okay, it's going. Maybe some people will join and even might ask questions. Let's see. And let me share with my screen. Entire screen. Okay, hope you can see this. And I can say this part of the board will be taken by my video, by my face. Actually, yes. Okay. Actually, it has a it had a beginning from my trying to understand what is group. No, actually, it started from understanding what is action. Action, it's how I was taught. It is, for example, we have group. Oh, we have a group acting on some set or some another object. But we are taught it is the set. So G group and A is set. And then I ask my question: what is action of A G acting on A? And then we were given definitions that we have G and we have homomorphism phi to the symmetry group of the set. It's set of all bijections A to A or the permutations of set, and this it sends element G to some particular bijection corresponding to this element phi G or phi G. And then I ask my question: what is homomorphism itself? Because I didn't get it. And what does it mean that it saves some group structure or some kind of structures? And I wrote myself on this paper that homomorphism maps that between two groups preserving its structure. And I asked myself, what is the structure of a group? Group structure, it's G. It consists of set and operation. Operation. And to make them together, to put them together, we define set of rules. Set of rules. It's closure, let's say closure, associativity, and what else? Identity, having identity, and also, what was it? And inverse. Inverse, of course. It must follow these four laws to form a group from the set. And then, what was my thoughts? My thoughts is, first of all, is it possible from any set, for any set define an operation that's agreed with these three laws, these four laws, I mean. And or shortly, Let's have a set G and set of operations theta. Okay, I defined like this. Okay, we have S. I called it S. It is set of sets. Set of sets and define theta as set of operations. Operations. Shins. And then I ask myself, is there one-to-one correspondence between S, one-to-one correspondence between S and theta, such that they form a group structure? They satisfy this group structure. I mean that for any G, such that for any G, G is, we can say, not as a group, but some set belonging to S, there exists operation operation Q belonging to a set of operations theta, such that this G and the Q group, or vice versa, because it's one to, it must be one-to-one correspondence, or for any operation Q in theta, Q in theta, there exists there exists such a G set in S, such that this G and the Q again form a group of form form a group. That is my question. Also, I find it interesting that we are looking at not the group, but we are thinking about what is group. I hope you can see this well. It's because my face might close it, this part. Okay, I will take in my mind. Okay, and then operation of the group. I asked here myself the question, how does the operation work? What is the hidden by operation in itself, keeping the group structure, keeping these four laws, satisfying these four laws. Investigation of fixed, for example, we have some fixed operation Q, and we need to investigate it for different sets and to see what does make corresponds of a set and operation valid by group structure. I mean that for what sets operation keep group structure and for what it doesn't. Question, question, question. For what? For what G in S, Q operation in the set of operations. Oh my god. Operation Q keeps group structure, keeps or sa- satisfies four laws of a group. And third, I see operation for a given set G as some uh, automorphism. But about third question, I already thought about it about automorphism. It's not correct. I would like to say in advance this question because automorphism is much stronger than just operation itself. And I thought about it because the word automorphism already implies map G to G that keeps the group structure. Also, by this way, we are going from beneath to up. Instead of going from beneath to up, we are going from up to down. By that, I mean, for example, when we are defining a group, I went from the beneath, from set and operation. Yes, going up to the group. Group. What if we'll go down to study what does this connection between them, how they form a group? So in a group, we can, of course, define automorphism of this group to itself to study the sets and operation, and from this our wave from up to down, we can get some information how the process from down to up is going. Yes, that's was interesting question. It's like a interesting perspective on the question, because from time to time, sometimes it's really helps to look at the question from inverse, from upside down. For example, I love the, I don't remember in which week I have read. It was, I think, in the beginning of the critique of pure reason. He said how the Copernicus, Emmanuel says how Copernicus, uh, what mainly did he do? He said that he just posed the question inversely. If before him it was thought that the suns and other planets are going from the around the star, around our Earth, but what if our Earth is rotating around some planet or some star, and it's totally changed the game? And it turns out this perspective, this question, was more productive than the previous question when the stars and planets were moving around the Earth. And I also had this question because of that. And also I was thinking we can reduce or expand set. For example, we have some operation. Let Q is operation, a set of operations. And maybe we don't need to look for, maybe we don't need to look for G in S. Maybe we can, for example, we choose arbitrarily some set, arbitrarily, arbitrarily some set, and we'll work on it, work on G, work on G. We are working, with this set in a way. So we are by working, I mean we reduce or expand it, set G in a way that the group that such that the G prime, the worked, we already worked on G somehow, and G prime and this Q will form a group. That was my idea actually. So, and here by G prime, let me say G prime is reduced or expanded G set. And by reducing and expanding, it already brings the notion, naturally, the notion of homology or cohomology to measure how much we expand it and how much we reduce it. Homology or cohomology. Homology. And how to measure our expansion, our reduction, in terms of that we are just considering how much we reduce it and we factorize it on how much it was, or vice versa, how much remained, so kernel, how much remained, and how much we expanded it, or how much, how the image of uh, our action on G, on the set G. Kernel under image. We factorize our kernel, what is not changed, and factorize it by what is changed. And um, this how can I say, this group or this object, and particularly its value, maybe its dimension. We didn't define a dimension, but it will give some notion about uh, how much we made the work on G. If it's big, we made a big work on G. If it's small or even trivial, we didn't do much on G. So the bigger this set, let's say, the bigger this notion, this object, is then the bigger work we did on G, that this G prime and Q form a group. If it's trivial or very small, it means that G's were more suitable to Q because we did less work. Yes. And I find it really interesting that we already bringing such interesting notions to the relatively simple question. Yes. And also, I here thought about uh, in a dual question. What I mean by dual, for example, in differential geometry, there is a vectors, set of vector space, and there is a to this with a natural mapping, the which makes the keeps the isomorphism the V vector space and the V star, which is dual space to it, the natural homomorphism, natural map between them, and um, this V star, it's a set, the vector space of linear forms on V, and this is set of vectors, and it is set of linear forms, linear forms, and in combination V and this omega or W and V gives some number. It might be in some field. Yes, so it's we can just think about, or when we are defining the pushback or pull, what was it? Push or pull back actions on the some manifold. So, for example, when we defined the differential of our map, we define a dual map. So if we're considering, I don't remember already much about it. I've learned it a few months ago. I didn't opened it yet. Yes, but in simple words, I mean we have some objects, objects, and some morphisms on it, some mappings on it, morphisms or mappings, or we can say some forms, as in this situation, forms. Yes. If we have some map like this, then in this dual space, this mapping will be turned, like a switched its direction. And my question was, because Q is operation on G, so what if you consider if you work on not the set G, but on operation Q? So instead of reducing or expanding G, we reduce or expand operation Q. By reducing or expanding Q, I mean some its image or kernel of this operation, of this mapping. But also we, of course, we here need to define what do we mean by image and kernel of the operation. And it's in theta. Also, again, if, for example, for the objects, we define it homology in this way, in a similar way, we can define cohomology. Co, it means like dual. Cohomology. Homology. Yes, it was also interesting to work on that. Nobody joined yet. Okay. Okay, let's move on. My next thing, it is actually what I was talking, what I was that just talked about. It was not the main topic actually. My main topic was about what is kernel and the image of action. Kernel and the image of action. And I have some papers that I wrote down all my thoughts, but it will be too long to share with all of you. So instead of that, I will consider some key points in my these notes. For example, consider G acting on set A, group and set. Let G consist of, let's consider firstly finite groups and finite sets. Consist of G1 and Gn elements. And A consists of A1 and AM. AM. And then I consider the matrix M, which was consisting of all the images like G1 acting on element A1, G1 acting on A2, and so on. Let me find the better one. Yes. And so on until G1 acting on AM. And here G2 acting on A1 and G2 acting on A2 and G2 acting on AM. And of course so on until Gn acting on A1. Here is the similar Jn acting on A2 and so on Jn acting on AM. And I wrote it down in this way. We can write in a, as I said in my notes, in row representation, row representation, presentation in a way that so we consider the column by column. So it's a G set at the group G acting on the one element A1, and here is G acting on element A2, so on and so forth, G acting on AM. And here I also wrote it down in a column representation. Column representation. In a way that, let's consider row by row. So it's G1 acting on set A, G2 acting on set A, and so on and so forth, Jn acting on set A. Transponent, of course, it's column. It's column. Let me write it down like this. I'm doing this because to save some space. I hope you understand it. And then it leads to me that we can write down M as G tensor multiplication with set A. Of course, you might attack me now, but means that me using the tensor multiplication really inappropriately, but it will ease my further thoughts, and I think this kind of notation will not be so deadful to my the further investigations. So let's just keep it. And then I define it the kernel of action and the kernel of action, kernel of image in a way, in this way. I define it. Let me consider, when we consider the action, we consider the homomorphism phi to symmetry of set A, such that I consider the kernel of phi in a way that it keeps for the one particular element of AI, in a way that it's all the G's in G group such that this G's keeps the AI fixed. AI fixed, and then for any AI, for the particular AI that we're considering, not for any, of course. For AI in A. for A. In A, I consider image of phi in AI, image of the our homomorphism, but on a particular element of set A, not the image of whole set, but the one particular element. So it's image, it's all the images of A, it's for any A in A such that A is equal to is equal to uh, G times AI for any G's in G. But this I find it that this can be obtained from the raw representation. Raw representation. What about the column representation? And then, like, all my thoughts, as you might notice, is just just seeing the things from like a wow, it looks similar. Let's do this. So yes, and I don't care about it because I find it really interesting. And the co-kernel. I defined co-kernel of phi on, but if we consider it on the A's element, then we consider G's elements. So I define in this way. Here I look at the words. I consider it on the words. Here it's all the elements that fixes AI. But what if we consider all the elements of AI that is fixed by GI? So it's all the elements for any A in A such that GI keeps them fixed. Keep fixed for GI in G. So it's a column representation because we look at the i's column, the i's the i's column here, or i's row, because it's column representation. That's why I call column representation. But we look at the row, the row of the uh, the matrix M. And then I had a problem, big problem, on defining co-image of phi and GI. Actually, I couldn't define it in a proper way because image of phi, I it's by definition it gives all the images of element AI in A by the actions of G belonging to G. So if we formulate it in terms of words in a dual universe, so co-image must give all the uh, well, let me find it. Where did I write it? Sorry. The sense element to other. Yeah. Yes, that's why I had even now I can't find, because on my notes even I couldn't formulate it in the proper words that it would sound valid. Yes. Oof. So in words, let's do it now. So if A was the image of phi in a particular point AI was all the images of AI by the actions of G. So co-image must also belong to this column representation. So co-image must contain it, because kernel. I was thinking I'm explaining my thoughts, the process of thinking. If kernel was consisting of G's, but co-kernel consisting of A's. So if A image consisting of elements A, so co-image must consist of elements of G for any G in G in a way that Gi acting on A must must be same as G acting on A for any A's in A. So I define it in a way that it's kind of fixed. Our, like they have the same image. All the G's that has the same image as Gi. You can visualize in this way. I will show you now. For example, what does it mean? Gi acting on A has the same image as G acting on A. It means, for example, we have G group, G1, for example, G2, G1, G2, G3, and so on. And we have set A, A1, A2, A3, and so on. G, A, and consider some permutations of A. I called it Pi or pi. Yes, it consists of all the permutations is A, AI1, AI2, and the AI3. So, for example, G1, let be G1. So G1 has image, for example, AI1, and G2 acting on this element has the same image. So G2 and G1 belong to this co-image. Yes, but we also want to, I didn't check, is the image or co-image really the subgroups of the corresponding G and A correspondingly. Let me now expand my board so I can write more. Yes. So I didn't check that co-image might be is it the subgroup of G? I didn't check. So if it's subgroup, it contain uh, must contain the identity element. Does it contain identity element? It's it's obvious to see, I think, that it doesn't. For example, for some arbitrary GI from G group, it doesn't work well. So that's why I didn't like. That's why I was kind of very suspicious about this definition. Maybe the co-image on the particular GI is not a group, a subgroup of G, but in total with the with the union of them, it might form a group. I didn't check, but that because of me being suspicious about this definition, I considered what defines our matrix A, and I came to the very beautiful diagram that represents the matrix M, and it is this diagram. I hope you can see this. Yes, this diagram. Yeah, my friend is texting me, but I think he's not already in chat. Yes. Okay. I matrix M. We have J. Wait. G, and we have phi map homomorphism to symmetry of A. And then I considered again another mapping. Yes, I called it P1. That is like projection map. It takes from G some arbitrary element G. And I considered also P2. P2. that takes some permutation of set A. I called it P. Oh, I call this P1 and this is P2. P2, P1, P1 of A, some permutation. And I consider the mapping psi of psi. And this is it must be commutative map. By commutative I mean phi and P1 must be equal to P2 and psi, like this. And this diagram defines matrix M, but in which way it defines? That's the question. Here, 1 minute, let me find it. I wrote it somewhere. I wrote it somewhere, but where? Where did I wrote it? Oh, here. Defines M. And it looks like it defines column by column or row by row. I thought about this, but I couldn't find it in my notes. So by this diagram, it's showing that if we'll go from like a P1 and psi, so it takes P1, it's G, some element. So it's either, I think it's row by row, and psi, it gives some permutation of A. So it's probably row by row. So it's a column, it defines in column representation. Where is it? Where's my diagram? It's here, yes. Defines row by row. Row by row. Row by row or column representation. Column representation. What if you consider to define the co-image? I was thinking if the matrix M shows the rules of G acting on set A, maybe there exists something which I call to myself co-action, that A kinda helps to reconstruct G. So I just consider the co-diagram, the dual diagram to this, in a way that G, the vertices are the same. Vertices are the same, G and the pi 1 of A, permutation of A. And I consider that just switch to all these edges in this way. It was psi, I called it psi star, psi star. And then it is P. It's because it's the dual notion to the projection. So I call this the, I don't know the name. It's I. Let's say I. I. Where is it? Yes. I2 and the I1. And this is phi star. This defines dual action or co-action. But it's very, very, how can I say, it is my definitions are very slippery, I would say, because under these diagrams there is no hidden thing yet. It's just some pictures. We need to still I need to still work on that to make it more precise. But I think it shows somehow that we can construct M or M I called M star, the matrix of coaction, and this will give us will give us give us the the definition of coimage. Coimage, and this is still question. But I need to still think about it. I will think. I will do it, and then now the main part. Main part is, let me find. And my question started from the simple question. For example, we have matrix M. How to get how to get kernel of, and then I here you may notice later that here I changed my way of approaching. Here it was more local local observation of the kernel on the image on a particular element of A. Here I am considering more globally. I'm considering the kernel of phi as the how the action globally. Previously, I considered the action more locally on the particular element of A. So here is globally kernel of action. And then I started to construct some sequences. Sequence. I can say the sequence 0, kernel, and the inclusion in G, or it's called in the geometry or topology, it's like a embedding, and the phi, and the symmetry of A, and then to the kernel of phi here, kernel of phi, and the co-kernel I call co-kernel of phi, co-kernel of phi, yes, and the co-kernel was, so if so, for example, kernel, I can say co-kernel because I can say symmetry of A, the permutation group of set A, and going surjectively to the co-kernel, because I had some feelings that it must be so, because here I define co-kernel in a way that it contains set of A's, elements of A, the set A. That's why I can say particular this sequence, and this is surjective map. It means this two, the double arrows means surjective. It's embedding, that's surjective map projection, I call P. And I considered the parts, by the short sequences in it, the one, and then two. I will try to not be very detailed in this part. Okay, I forgot one part. G to co-kernel is the third part, and symmetry co-kernel is the fourth part. And let's say here it's injective and surjective. I define it co-kernel such that this pi is surjective. So here I am, instead of how can I say, trying to construct co-kernel. I am defining co-kernel. That's a very slight difference, but very crucial, I would say. If you can't solve some problem, try to define it in a way that it's possible to solve it. It was some kind of my logic when I was doing this. And we can say that in the first, for example, in the first part, it is exact at exact. So I call this 0, 1, 0, 2. Exact at kernel phi, because the image of 0, it is, since the this I is injective, so it corresponds to kernel of this I. So that's why it's exact when the image um, corresponds, not corresponds, but equal to the kernel. And the force, this force element of force source short sequence in this long sequence. So it's also exact at co-kernel phi. Co-kernel phi, because 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 image of pi, image image of phi, image of pi, it's co-kernel of phi. It's not writing co-kernel phi, and which is equal to kernel of 0, 2. That's why it's exact at co-kernel phi. And the more hardest part were the second and the third chains in this sequence. Third, I asked myself, and I can say the first, second one, yes. Yes, it was easy, relatively, because I is injective. So then the image of I, it was kind of equal to the kernel of phi. And the kernel of phi, so let's say isomorphic, let's say kernel of phi, and it's equal to kernel of phi, kernel of phi. So we got the equality. So that's why it's exact exact at G. Third, it's the hardest one. I ask myself, is is image of phi equal to kernel pi? And then I ask myself, let's be more polite, less strict. Is image contained in kernel? Is image of phi contained in kernel pi? So at least we can define some notions of homology, cohomology to measure how much it differs, how much it fails to be injective or surjective. Yes. And then I also couldn't show any of this, but then I said, okay, I can show this. I couldn't show this. But what if I will say, let I define co-kernel co-kernel in a way that that image of phi is equal to kernel pi. Kernel pi, image of phi, kernel pi. So then it's obvious to see, because it's surjective map, pi is surjective surjective, then we can see that um, co-kernel will be isomorphic to the symmetry of A divided by or factorized the by the kernel of pi. And because we have equality of them, so symmetry of A by factorized by image of phi. So we got this equality, kernel phi and symmetry of A phi. Symmetry of A factorized by image of phi. So that's kind of interesting, I find it. So I defined co-kernel in a way such that this equality will hold, must hold. Yes, because image of phi it's always contained in symmetry of A. So it's only question of the map pi, and the pi is maps to the co-kernel. So I can define co-kernel its structure in a way that its kernel will be similar, will be same as image of phi. Yes, and we got the definition of co-kernel, and it looks for me that it's quite valid because it's we're factorized by the images. What does it mean by that that we factorize by the image of phi? So because image of phi it's all the permutations, maybe it will give some information about our previous definition co-kernel because it's only for the local structure. Maybe it will give some information about this, about local structure, I was thinking. But by itself, even without the being used afterwards, but it's by itself, it's I find it interesting. And of course, I will not lie. I have seen and then I have checked what is the definition of co-kernel, and it turns out it's the same as I did here. So I was also quite happy by seeing this. Yes, I might be cancelled because I'm quite long here again, as usual. Yes, so we already have done work with kernel and co-kernel, but my main question was about what about can we do the same with image and co-image? What about image and co-image? Co-image. That's more interesting question. Here I considered this sequence 0, 1 going to the image of phi, and it's injectively embedding in the symmetry of A. Why I considered this map that it's image going to the symmetry because but initially I considered quite mm, I mean the inverse situation when the symmetry going to the image. But I find that if we consider the mapping G going to the symmetry, image is kind of inserted, embedded in symmetry. So it's more natural that image is embedded in the symmetry, not the symmetry is packed on the image. It will lose the information. So instead, we'll insert the image in this to not lose information, but to more get the information. I and instead of considering phi because it's from the symmetry going to the G, I consider it phi star and going to the surjectively going to the co-image. I I did this all the by the analogy of the previous sequence co-image of phi by the map pi and going to the sum 0 by 0 2. Okay, then let's continue. Also, I break this into the parts, this part, and then this part, second, third, and fourth. I will not write the numbers. Maybe one, two, three, four. So first, it's obvious as in the previous situation, it's exact. It's exact at image, at image phi. Because also the image of 0 1 is just identity of image phi, and because I is injective, so kernel of I is also identity, so they equal, that's why it's exact. So fourth also exact at co-image of phi, again with the similar case as it was before in the um, previous sequence. And the more questions arise from the second and third part, the short sequences of second and third short sequences. I also ask my question, what is the relation between image of phi, image of, oh my God, why it's not writing, image of I, and the kernel of phi star? What is the relation between them? That's interesting question, I find, because the it's injective. So image of I, you can say it's just equal to the image of phi. And also I could prove, I will not provide the proof because it's too long. It will take too much time. I just found that the image of I is contained in the kernel of phi star. I proved, I will just a schematic. It's because I assumed that image, I initially thought that it must be equal to, in order to the sequence to be exact at symmetry of A, as I assumed that. So maybe image of I is equal to kernel of phi star, but I could prove it. I could prove it only for this in a way that let's assume that there exists uh, there exists such a thing, image that is not in kernel. So the kernel is contained in image. And then I did something and I came to the contradiction. That's why the image must be contained in the kernel. So it must be like this. Yes, image is subset of kernel. I could only prove this. So we can measure how much it's measure how much it differs, measure of how much we can how much it fails um, to be injective in this case. Yes. Ooh. Okay, for this it is. And also here, when I say for example here, image of, for example, before, image of phi is equal to kernel pi. Kernel, we know it's a natural, the normal subgroup of symmetry of A. Symmetry of A. But by this equality, it means that image of phi must be also normal subgroup of symmetry of A. But generally, image of phi is not normal subgroup. So what what we got here? What does it mean? And I got some my own interpretations. What does it mean? What does it mean being exact at at symmetry of A. Yes, I see one solution. In assumption is that image of action is always normal subgroup. In assumption is that image of action is always normal subgroup, but I didn't because it's doesn't seem very valid. Or maybe for the sets or and its symmetry of A, it might not be realized. Yes, my solution is that this equality might not be realized for the set and its symmetry group because it's too broad, too general, and it's not restricted. But it might happen that A is group, and instead we can uh, consider automorphism of A and the inner automorphisms of A. It was my resolution of this problem. I will come back to this a little bit later. Oh, that's good. And then third, it's the same trick as it was before. I define define co-image of phi such that kernel of pi is equal to image of image of phi star. So if so, we'll get that image of pi is isomorphic. Oh my god, is isomorphic or equal to the g factorized by kernel pi by the first isomorphism theorem, and it's equal to g factorized by image of phi prime. And from this, and kernel pi kernel of pi, it's I said it's g, and I assumed here assumption it's not valid. It might not be valid, it might fail here. It's very crucial step. G factorized by the kernel of phi, because I assume that the image and kernel are the same. Image of dual action is the same as kernel of action. The image of coaction is the same as kernel of action, but it is very slippery here. So let's be cautious. I will explain why and why it might not hold. Yes, so we got, oh, it's co-image. Image of pi is co-image of is equal to co-image of phi. Yes, because it's surjective map. So we get co-image, and it's equal to this g factorized by kernel phi. And I also checked it must be right. Actually, here I did it in vice versa. I just checked what is co-image, and then I wanted to get the g factorized by kernel phi by definition that I saw in Wikipedia. And I got this. But here is I need to be more careful. And let me explain what else I did here. But where is this? Where did I write it? I here let me find our phi. Phi is this. It's phi. Yes. But it's here. I found. Also about the notions of embedding and the immersion. Embedding is a global. Embedding. It's a global. And the immersion is local. Embedding is a global when we, for example, we have. I also learned this when I was studying differential geometry. Embedding it's when we have the whole space and we embed it inside one another space. Immersion is a local embedding. We have some space and we have point on it and local the neighborhood of it, and we do the embedding to the another local neighborhood of the point in the another space. Yes, by that what I mean is that image, as I mentioned before, image of phi at point AI, it might correspond to immersion as a local embedding. Embedding is just image of phi. Yes. But here also many questions arise. What do you mean by locality? What is the neighborhood of the point? And I'm thinking about it. Maybe if we consider S and we define the topology on it, and then we can define the neighborhood of it, and it will be fine. But I didn't yet work on it. Yes, and I here I consider the image of phi prime, the phi star, and the of kernel phi. Here, I assume that they are equal. Here, you see, I assume that they are equal, but I assume, but what if they are not? Also the same, similar to this, I could show that image of phi star is only contained in kernel phi, but I couldn't show the inverse of it because I defined phi phi star the composition with phi is equal to which is the identity element of G, and vice versa, phi times phi star composition with it gives identity permutation, which is element of symmetry of A. It's here for any G, and it is here for any permutation, for any psi, I said, in this, in symmetry of A. But also, I maybe it's okay if I define it like this. But if so, I can measure how much it differs kernel phi by image of phi star. I can see how much it fails to be equal. To measure how much it fails to be equal, to be trivial. To be trivial, if it's trivial, this is the factor group. So then they are equal. Or or in order to measure how much image and kernel differ from each other, and we define it the phi star and the phi in this way. Maybe it might be, as I said before, we restrict symmetry of A, restrict SA, let's say SA, not to the whole thing, but to the automorphisms of A, to automorphisms of A. Of course, it's very, very inappropriate to say automorphisms of A because we can't define, because automorphism, it's by its definition requires group structures, that it keeps the group structure, but A is just set, so it cannot define this. But let me continue still. To automorphism of A, in order to get to get to get image of phi is equal to kernel phi star, or vice versa, the same here, image of phi star to the kernel phi. Or maybe, as I said before, we can restrict the set A Instead of considering set, we consider group, and then we can define automorphism on it, and it will hold. But so then we can make our long sequence exact at each of these elements. And why it's would be great to restrict symmetry to the automorphism of A, because we already know that inner automorphisms inner automorphisms is a normal subgroup of automorphisms of some group or set A, let's say set, but it's not right as, and it will be kernel phi prime, and it will be very natural that kernel will be equal to this, and which is the kernel is normal subgroup of the group, and it will be very natural. Yes, I'm still thinking about it. I'm in the process. I just want to share with these beautiful things that might arise with this diagram and with these sequences and these notions about that we can consider groups and the dual objects, dual things to it, and work with them. And it's very beautiful. And also this idea of constructing the group from the set and the operation and going down from going instead of going up. That's also I find it really interesting. Yes. For today, I think that's all. I will still work. I hope if I'm not bored, I will not be bored of this. Yes. Yes. And thank you for the video. Bye bye.